Welcome to the deep dive. Imagine trying to orchestrate, say, a huge smart factory floor, thousands of machines, all needing to work together perfectly. Or, managing critical infrastructure that absolutely cannot fail.
Yeah, the complexity is just enormous.
Exactly. And the old ways of controlling things, they struggle with that scale and complexity.
They really do.
So today, we're diving into IEC 61499. It's a standard that's really rethinking industrial control. Almost like how object-oriented programming changed everything for software development years ago.
That's a really good analogy, actually.
We'll be looking at its function blocks
Yeah.
and their instances, or, in German, Funktionsbaustein und seine Instanzen, and exploring how these ideas bring some pretty sophisticated object-oriented thinking right into industrial automation. We're using an excerpt from the DIN 614991 standard, the architecture part, as our guide,
Right, the foundational document.
our mission, to show you how these, well, seemingly abstract concepts tackle those really tough, real-world industrial problems. Let's dig in.
Sounds good.
Okay, so industrial control systems, IEC 61499. Now, for people who know the field, this standard is really built for distributed control.
Absolutely. That's its core purpose.
So what's the fundamental piece? What exactly is a function block here?
It's defined as a functional software unit. You can think of it as a kind of self-contained, intelligent little module.
Okay.
What makes it unique is that it bundles together a named copy of a data structure with the operations that work on that data.
Right.
And crucially, these aren't just for controlling one machine in isolation. They're specifically engineered for distributed systems. That lets your control applications stretch across multiple devices, multiple resources, communicating across the whole setup.
So it's not just a renaming of old concepts.
Oh, definitely not. It's important to grasp this difference. Unlike something like IEC 61131-3, which historically focused more on a single PLC.
The single controller box?
Yeah, exactly. IEC 61499 function blocks are designed from the ground up for distribution. Their properties, like event-driven execution and these sort of implicit communication pathways, they're fundamentally different.
Okay.
And that's what allows an application to seamlessly span across different devices, maybe even ones far apart geographically. It's really a different way of thinking, a paradigm shift, you could say.
That distribution aspect, that really jumps out. And within that, the standard mentions types and instances. Now, that's familiar from software, but how does it work for function blocks in 61499? What's the relationship between a function block type and a function block instance?
It's a really foundational distinction. Think of it like a blueprint versus the actual building made from it.
Okay, yeah, that helps.
The function block type, that is the blueprint, or the template. It's the software element defining all the common stuff.
Right.
The event inputs, outputs, data inputs, outputs, internal variables that all copies made from it will share. It's the generic definition.
Template.
Then the function block instance is the specific individual named copy. It's a realization of that blueprint. It gets all the attributes defined by its type.
And making one is called?
Instantiation. That's the process of creating that unique functional object within the system from the type definition.
Right, instantiation.
And this leads to something critical, especially when you're talking industrial scale. The standard lays out a very clear naming structure. You use the application name, any sub-application name, and then the specific function block instance name.
Why is that naming so important?
Well, imagine a huge, complex factory, thousands of these things interacting. Without a unique name for every single function block instance,
Chaos.
pretty much, how would you track down a problem or manage updates? This unique identification is absolutely essential for managing these big, complex, often distributed systems effectively. You need to know exactly which component you're dealing with.
Makes perfect sense. Okay, so we have the blueprint, the type, and the unique creation, the instance. With that clear, it seems function blocks aren't all the same. The standard talks about different flavors, right? Basic composite, service interface, and sub-applications.
Exactly. Each one has a distinct role in building up the system.
So what makes each one unique? Let's start with basic.
Okay, the basic function block type. As the name suggests, it's the simplest. The standard says it's not decomposable into further function blocks. It's the bedrock.
And how does it work?
At its core, it uses something called an execution control chart, or ECC, that governs how its internal algorithms get executed based on events.
Okay.
And one interesting detail, an update in the standard, is that basic FBs can now have local temporary variables inside their algorithms.
Temporary. Meaning?
Meaning they only exist for a single run of that algorithm. They get initialized, used, and then they're gone. Their values don't stick around for the next time the algorithm runs.
Ah, okay. Why is that significant?
Well, it helps prevent some common problems in concurrent systems, like accidentally messing up data because something else ran in between, or race conditions. It keeps each execution clean and predictable, sort of like pure functions in programming.
Right. Avoid side effects from lingering data.
Yeah.
Got it. So that's basic. What about composite?
Composite function block types are where the modularity really starts to pay off. Instead of having its own fundamental algorithms, its logic and control are defined by linking together other function blocks, could be basic ones, or even other composites.
Ah, so it's like building with Legos.
Exactly like that. You express its functionality through data connections and event connections between the components inside it. It lets you build up complex behaviors from smaller, reusable parts, a higher-level module, essentially.
Okay, modular building blocks. Then service interface. That sounds different.
It is. A service interface function block has a specific job to offer one or more services to an application.
What kind of service?
Think about interacting with things outside the core logic, like specific hardware or maybe a network protocol or even a database. This block works by mapping primitives, which are like abstract universal commands like start, stop, get data to its own event, and data inputs and outputs.
So it sort of hides the messy details.
Precisely. It abstracts away the low-level complexity of how those commands actually get sent or received, giving you a standard way to talk to external things.
Neat. Okay, one more. Sub-applications. How do they fit in?
Sub-application types are quite similar to composite FBs in that their body is made of interconnected components, function blocks, and other sub-applications.
So they can contain each other, nested.
Yes,
Yeah.
exactly. They're nestable. But the really key thing is their built-in support for distribution. Sub-applications can be explicitly distributed over several resources, meaning different physical devices.
Ah, so that's how you spread the application out.
Right. This nesting and distribution allows for a self-similar hierarchy in your system design. It's vital for building those really big, multi-layered applications that need to run across a wide distributed environment.
It sounds like a lot of thought went into making these function blocks self-contained units. What's actually happening inside them? How do they manage their own logic, their own data? And why is that internal structure so important for the system as a whole, for things like reliability?
That internal structure is, it's fundamental to how they work and why they're robust. Inside, function blocks can hold internal variables, sometimes called state information.
And unlike those temporary variables in basic FBs.
Right, these ones persist. Their values stick around between times the block's algorithms run. This is obviously critical for keeping track of what's happening in an ongoing industrial process.
Okay, state memory.
But here's the crucial design choice. Those internal variables, they are not accessible through data flow connections from outside the function block.
Ah, hidden away.
Exactly. That's a key part of encapsulation, keeping the internal workings private and controlled. You interact through the defined inputs and outputs, not by poking around inside.
And the logic itself, the algorithms.
The algorithms are just defined as that finite set of well-defined rules to solve a problem. From the outside, you don't necessarily need to know the exact code, you just rely on the interface, what the supplier formally describes. How they run might change based on inputs in that internal state, but the behavior should be predictable.
And you mentioned the ECC again for basic blocks.
Yes, the execution control chart. It's that graphical or text representation showing the cause and effect between inputs, outputs, and which algorithm runs when.
And the standard improved this.
Significantly, yes. The standard has improved and extended how ECCs behave. The conditions for moving between states are now clearly described using UML syntax.
UML, like in software modeling.
The very same. This strict, formal way of defining the transitions avoids misinterpretation. In complex industrial settings, especially safety-critical ones, you just can't afford ambiguity. Clarity is paramount.
So putting it together, this internal structure, the hidden state, the defined algorithms, the clear ECC logic, it gives you predictability, helps with maintenance. But does that encapsulation ever make troubleshooting harder? If you can't easily peek inside from the outside, how do you figure out what went wrong in a live system?
That's a really practical question, and actually the design often makes it easier, maybe counterintuitively.
How so?
Well, because the interfaces are so well defined and the internal behavior is predictable via the ECC, problems tend to be localized. You can't directly fiddle with internal variables from outside, sure, but think about, say, a pharmaceutical process. A tiny glitch could ruin a whole batch.
Right, high stakes.
With function blocks, because they're encapsulated, you can often isolate a segment of your logic. Test its inputs and outputs, check its ECC state transitions without necessarily bringing down the whole line or risking interactions with unrelated parts.
So you focus on the defined boundaries.
Exactly. Debugging focuses on those interfaces and the defined logic paths, not chasing some obscure internal variable change that rippled through a huge monolithic program. So this structure, this segmentation, actually makes debugging complex systems more manageable, not less.
That's a really strong point. Okay, so we've got types, instances, these self-contained units with their hidden data and logic. For anyone with a software background, this is starting to sound very much like object-oriented programming, right? Was that on purpose?
Oh, absolutely intentional. This is really where IEC 61499 stands out and shows its modern approach to industrial control. It's not just a coincidence.
So the standard acknowledges this.
Explicitly, if you look in Annex C of the standard, it actually presents object models using UML, the Unified Modeling Language.
Wow, okay.
So yeah, they deliberately aligned it with established object-oriented principles. The connection is direct.
So how do the concepts map?
The parallels are really clear. The function block type, that's essentially your class in OOP terms. It's the blueprint.
Right.
And the function block instance, that is the object. A specific named realization of that class with its own state. Just like you can have many car objects created from a car class, you instantiate many function block instances from a single function block type.
Okay, type is class, instance is object. What else?
Well, encapsulation, like we just discussed, that invisibility of the internal variables and algorithms, that's a classic OOP cornerstone. Hiding the internal state, protecting it, interacting only through defined interfaces. It promotes better design, less coupling between components.
Makes sense.
And then there's composition. Remember the composite function blocks and sub-applications?
Yeah, building bigger blocks from smaller
No.
ones.
That's composition in action. It's a really powerful OOP design pattern, building complex things by assembling simpler, modular, often reusable parts. It makes systems easier to manage, easier to test, easier to scale.
So class object, encapsulation, composition. Anything else?
One more thing that's really powerful, although maybe not a core OOP concept itself, is how the standard handles distribution.
Spreading the application across devices.
Exactly. These object-like function blocks can be distributed across multiple physical devices and resources. They act as atomic units for distribution. This is a huge step forward for industrial control, allowing for systems that are inherently distributed, scalable, and reconfigurable.
Compared to older methods.
Oh, yeah. If you're used to traditional PLC programming, this event-driven distributed model of IEC 61499 is a whole different world. It brings a level of flexibility that was just really hard, if not impossible, to achieve before.
It really does sound like a sophisticated leap, borrowing directly from proven software engineering ideas. So we've talked about building these systems, but what about managing them over their whole life? You know, in the real world, things change, need updates, maintenance. Systems aren't static.
That's another critical area the standard addresses, the system life cycle. It explicitly recognizes that systems, the devices they run on, the resources, the applications themselves, they all go through phases: design, commissioning, operation, maintenance.
Right, the whole journey.
And to handle this, the standard defines special types of function blocks called management function blocks.
Management blocks, what do they do?
They're not for the primary control logic. Instead, they provide the hooks for runtime control and management of the applications, resources, and devices.
Like what kind of control?
Things like programmatically creating new function block instances, initializing them, starting or stopping them, even deleting them, plus querying their status, checking connections.
So you can change the running system.
Exactly. A management function block could, for example, trigger a cold start or a warm start of a resource, or Maybe dynamically add or remove parts of the control logic without having to shut everything down.
Wow, that's powerful.
It really is. It means that whole object-oriented idea doesn't just stop at the initial design. It extends right into the management and maintenance of these functional units while the system is live.
Okay.
It's about enabling these complex systems to be dynamic, to be adjusted, updated, maintained without always needing a full stop, which is, essential for the kind of agile, responsive manufacturing and infrastructure we need today.
So let's try to wrap this up. If we recap our deep dive, IEC 61499 isn't just about writing control code in the old way. It's using these powerful function blocks that act like, well, intelligent, self-contained software components.
Modular units.
And that clear difference between types and instances, plus features like encapsulation and composition, it's directly mirroring those really elegant ideas from object-oriented programming.
It really is a direct mapping of those concepts into the industrial domain.
And the key takeaway for you listening is that this isn't just theory. It's not academic. This is what makes it possible to build highly modular, truly distributed, and dynamically manageable automation systems.
Yeah, systems that can adapt and scale up for the really complex industrial processes we see now and we'll see more of.
From smart factories to critical infrastructure, it's about how the components behave, how they connect, and crucially, how they can be managed across the whole system, even while running.
And maybe stepping back just one final step, think about these core ideas. Types giving rise to instances, blueprints creating unique functional objects that interact.
Yeah.
Isn't that kind of how we organize complex information everywhere, not just in factories, but maybe even in our own thinking? Moving from general concepts, the types, to specific applications or examples, instances. This paradigm of modularity, interaction, encapsulation. It's a pretty fundamental pattern once you start looking for it.
That's a fascinating thought to leave people with. From factory control to maybe how we structure knowledge itself. So what stood out to you from today's deep dive on function blocks, instances, and the object-oriented soul of IEC 61499? What other complex topics are you curious about? Let us know and join us next time on the deep dive.